Okay, hi everybody. Welcome to our next seminar for XFC 2024. We've had several so far, including ones on fuzzy systems, gradient-free optimization of fuzzy systems, an intro to the game that we'll be using to train agents, Kessler, and then we recently also had a talk on explainable AI given by Dr. Scott Dick. Our speaker today is Dr. Barnabas Bede from DigiPen Institute. He earned his PhD in mathematics from, I mispronounce this every time, but I'll do my best, Barnabas Bede, and Barnabas can correct me afterwards. University in Romania. Oh, well, at least I got it close. His research interests primarily include fuzzy sets, fuzzy logic, and image processing. He's on the editorial board member for the journals Fuzzy Sets and Systems and Information Sciences, and he joined DigiPen after holding positions in Romania, the University of Texas at El Paso, and the University of Texas Pan American. At DigiPen, he focuses on developing class materials for fuzzy sets and various topics in mathematical analysis. He's also heavily involved in NAFIPS, the North American Fuzzy Information Processing Society, where he's heavily involved in both research and organization. He also contributes to associated projects like this one, the Explainable Fuzzy Challenge, which is open to any university level student to learn more about both fuzzy systems and how to develop them for different types of systems, different types of problems, I should say. So with that, I'll hand it over to Dr. Bede to talk to us today about backpropagation, which is or gradient-based methods, I should say, of optimization for fuzzy systems.
Thank you very much, Tim, for the great for the introduction, and thanks for the opportunity again. So I know that you've got an awesome introduction into fuzzy sets and fuzzy systems, and you have seen a lot of examples how you can build a fuzzy system based on basically how you can train a fuzzy system using genetic algorithms. Today we will talk about how you can build them using gradient-based optimization techniques on the fuzzy systems. Yes, so just a quick check. Can you see my slides?
We see Adobe Acrobat at the moment, but it's just blank.
It's blank. Oh,
yeah. For me, we only see the top bar that says gradient-based optimization, but the rest of the window appears to be blank.
All right, let me try again.
Okay, now we see your desktop.
Oh, okay. So yeah, let me find the right window now. Can you see now the presentation? Or
yes.
Now full slide. Now it's full slide.
Yep. Yep. We see your title slide.
Thank you. So let's start with basically we will overview what is gradient-based learning, and then overview deep learning and basically how it works. Then fuzzy systems, specifically Takagi Sugeno Kang fuzzy systems, and then basically how we can do gradient-based learning for those. Yes. So basically, yeah, so as an introduction, we have here machine learning is typically a black box type of algorithm. So, for example, in the modern ChatGPT applications, type applications, you don't really understand where exactly one decision comes from and what led to the current output. Yeah, so in an explainable AI, we want to optimize to explain basically what we are learning. So our goal is to replace black box based techniques with interpretable methods such as fuzzy systems. With fuzzy systems, we saw that we can basically build rule bases, and the rule bases then can be explainable and understandable by the human operators. But how can we learn those rule bases? Well, based on gradient methods. That's the goal of today's topic. So several machine learning algorithms rely on the gradient concept. So assuming that we have here a vector field f of x and y, yes, z equals z is f of x and y, and then z is displayed as different level curves on the graph. So outside we would have z equal 1, then z equal 2, 3, so on and so forth, and inside with the highest one, or it could be backwards, saying this is z equal 5, 4, 3, 2, 1, 0 in the middle. So this is basically gradient, displaying the gradient field, displaying the vector, yeah, displaying the vector valued function f of x, y in plane. So how does this connect to machine learning? You can imagine this to be the error graph of a function. And the error graph basically saying the error is larger if we have the parameter settings here, smaller, smaller, smaller. So the error is optimized when you have basically a minimum value in this function. So how do we search for a minimum value? Yeah, it's based on the gradient of the vector field. Now it's provable in math that the gradient, which is basically the derivatives of the function with respect to the parameters. So it's a vector that has basically components to be the derivatives with respect to different parameters. So that always perpendicular to the level curves of the point. So this blue little vector over here is perpendicular to the level curve. Now, actually, this shows that our gradient direction is always the direction of steepest ascent on the surface. So I could go up this way on the surface. Yeah, now the opposite to that, we have the negative gradient, and the negative gradient always leads to the steepest descent on the surface. So imagining that we have basically a graph, maybe I should do this in my OneNote page. Just a quick fix. I'm going to open a OneNote document real quick to be able to draw on it. Yes, so here we go. Yeah, this is better. Can you see my OneNote page?
Yep.
Awesome. So the gradient basically so this is the function, and we have 5, 4, 3, 2, 1, 0, -1. Well, I should have started with 6 to have 0 the minimum, but we can have negative value in the minimum. So if I want to find the minimum point of this function, then the gradient shows the direction upwards on the surface. The opposite to gradient, yes, so minus nabla f, yes, that's the notation for the gradient. That shows the negative direction, negative the steepest descent direction. So imagining that I have here a point, and I could do small steps in the direction opposite to the gradient, basically every step to reach the minimum value. Yes, so that basically gives us an update rule for all parameters. Let's say the parameters all together are organized as a vector W. And this is the W new values are going to be W old values minus the gradient of the function. But the gradient could be large, so it could be this large, and then I'm doing two large steps. And I'm gonna go away somewhere in the universe now. So what I'm gonna do, I'm gonna multiply with a little scalar over there. So the gradient update or gradient descent method is working like this. This parameter eta is a small number, typically 0.01 or things like that. So you could set a value like this to the value eta, and it's going to do two small steps towards reaching the minimum value of the gradient. Yes, so that's how you can visualize the gradient descent method. Let's go back to here. So gradient descent method helps you optimize for the given parameter set. But you could do it parameter by parameter. Yes, so each parameter you optimize with the component in the given direction of the parameter. Yes. So now gradient-based learning. There are two basic steps in gradient-based learning. The first one was step by step. Yes, as we explained that. Yes, so this was later on now. Okay, so there is also least squares method. So least squares method, let's go over least squares method to see this example as well. Yes, so least squares method tries to minimize an error function. So let's look at the error function to be 1/2 xw minus y. So what's going on here? I want to minimize, this is the error. XW is the output of my model and Y is the actual output that I want to get. For example, I want to predict where to shoot with the spaceship, yes. And I have a set of parameters which will determine that, yes. And well, I will have an error, and we could optimize that error. Basically, this is my model output where I want to shoot and where actually as it happens to be, and then the difference squared should be minimized between them. So how to minimize that? There is a one formula for it. This is the parameters that minimize the error are given by this formula. Let me give you how you can get that formula. That's an interesting little math trick that I like, so I can show you that. Here we go. So I have this formula J equal 1/2 xw minus y squared. Y is what we want to get, and xw is our prediction. Yes, prediction. This is what we need to get. Or prediction, this is a actual value. Or desired output, let's put it this way, desired output. So to minimize that, the best minimizing method is when I have equality. So when xw is equal to y, I get 0. So I cannot have that, but I could get close to it by the following trick. I could multiply both sides by x to the minus 1 matrix. Yes. And then x to the minus 1 times x is a square matrix. X, typically, predictions will have lots of data points. So you will have a lot more rows in this matrix than columns. So this is not an invertible matrix. But x to the minus 1, sorry, x transpose, not x minus 1. X transpose, I went ahead of myself a little bit here. When I multiply it by x transpose times x is going to be always a square matrix. When I have a square matrix, that's when I can invert it. So I'm going to take the inverse of that and multiply it to both sides. So xtx to the minus 1 multiplied to xtx and w equal xtx to the minus 1 times xt times y. We can see that these cancel out each other, and we've got w equal xtx to the minus 1 xty. So this is basically called the normal equation, and it gives you a method to directly calculate the best one. So it's known that this minimizes error. So this equation minimizes the error directly with a one-step method. Well, what is the problem with it? Yes, sometimes this matrix is not invertible. Also, there is no solution which will make this error to be 0. So the error will never be 0. So this is a formal calculation, but this matrix is the best that it can actually achieve. So least squares method gives you a one-step method that basically gets you to the minimum point. So least squares method from here, let's put it this way, least squares method from any value, you get directly the best possible. Yes. The gradient descent is not like that. Yes, let me go back here. Yeah, so here's the trick that I was showing you. Yeah, so we do xw equal y, xtx, we multiply xt both sides, then multiply the inverse matrix from both sides. Okay, now we are going to explain one more time the gradient descent method, and now it's the deployed component by component. So we have w, well, initially we worked with the whole vector. Now we can see that each component we can actually break down, and here these these del E del wk are the parameters are the components of the gradient vector. Yes. Okay, now let's go over how deep learning works and to understand basically how we can construct packages to gain systems that learn. So neural network, yeah, in its expanded, well, in a one layer neural network in the given setting can be written by the following formula. Nn of x is w0 plus a combination of certain weights, wi, times the output of the so-called neurons. Each of these constitute a given neuron. Those are combined in here. In the neuron, we apply function phi, which is called an activation function. The activation function could be different functions. Typically could be ReLU or yeah, so it's typically a sigmoidal function that makes a switch from 0 to 1 smoothly, or could be a ReLU function which makes a switch from 0 to a linear function in a certain way. So Backpropagation algorithm is basically the core of deep learning. So when you train a neural network to do anything, you use backpropagation algorithm, which is nothing else but a fancy way to do gradient descent learning on a structure that is more complicated than that. Yes, so the basis of this can be seen here. So when you have two neurons that are connected to each other, let me just transfer this to my notes quickly. No, that's not the right thing that I wanted to do. My intention is not to make everyone dizzy. Sorry about that. That's a side effect. So let's assume that we have an input layer, one intermediate layer. Let's say this is layer L of the network, and this is layer L+1 of the network. How can I do backpropagation in here? So this outputs, let's say OK, as the output of the neuron at number K at a gradient. So now let's assume that we know the error gradient with respect to OK. So how do we achieve that? We're going back propagate the error from the last layer. In the last layer, I'm going to know what's the error because actually I have the prediction, I have the actual value, and I can compare, take the difference and square it. Yes, so prediction, actual value, square it. In the last layer, I know that. And how can I go from next layer to previous layer is here. So I know, let's say that I know this del E del OK. And then I want to propagate that to OJ. So I want to calculate del E del OJ. Let me switch to a better visible color. Del E del OJ. Yes. I want to get to that. So let's start with del E del OK. OK is going to be basically, yeah, let's say that we want to calculate del E del OJ directly. So I'm going to have here, so how can I calculate del E del OJ? So E depends on OK. So I could go this way. I could calculate the error of E with respect to OK. So I'm going to apply chain rule here. OK depends on ZK. Yes, del OK, that depends on ZK. Yes. Then ZK depends on OJ through this WKJ. So I'm going to go del ZK, del OJ. Yes. So at the end of the day, well, of course, at this point, I need to sum up all the dependencies where OJ makes a difference. Yes. So I could go a summation with respect to K being all neurons in this given layer. I'm just going to say summation over K, where K represents all neurons in this next layer. So basically, when I calculate del E del OJ, I could go down this path. And well, let's make this a little more explicit here, del E del OK. Let's assume that we know this one because we backpropagate. So we know the last layer. When I know the last layer, I can go to the last but first, last but second, so on and so forth. And I assume that I arrive to this layer L+1. At this point, I'm going to get OK derivative with respect to ZK is just phi derivative. Yes, because phi is a function that takes in ZK and outputs OK. And ZK OJ, ZK depends on OJ through WKJ, which will be the weights of the neural network. So basically, if I know del E del OK, all of them in the next layer, I can calculate all of those error gradients in the previous layer. And then if I want to calculate the error gradient with respect to the parameters of my network WKJ, then I can do the same with the same method. Yes, so I go down del E del OK, then del OK, del ZK, then del ZK, del WKJ. Yes. At this point, I'm going to be able to calculate, for example, all these values, and I can calculate this one. Once I know that one, I can backpropagate WKJ using the well-known method that we described above, the gradient descent method. So WKJ new value is the old value minus some constant coefficients times del WKJ. So this is basically the basis of deep learning. Yes, of course, there's a lot more to say about that, so would need more work, but this is the idea, the general idea of why deep learning works. So now how that translates into fuzzy systems, we will work just on one layer, but yeah, let's refresh a little bit Mamdani fuzzy systems. Yes, so Mamdani fuzzy systems are of the form, are based on fuzzy rules of the form if antecedent, then consequence. If asteroid is near, then threat level is high, for example. That could be a very easy rule to formulate. Or also, if the music is loud, then the neighbors are annoyed. A fuzzy rule base can be, now the general form of that, if X is AI and Y is BI, then Z is CI, where AI are antecedents from a certain universe of discourse. Let's say this is music. Music could be loud, decent, or soft, and Y could be wall thickness. Wall is thin, wall is thick, wall is moderately thick. Then music is going to be, neighbors are going to be annoyed or less annoyed. Could be another fuzzy set that we could describe. So Mamdani systems can be calculated as we have you have already seen, based on the following type of calculation. You calculate the firing level of each rule. Yes, so you calculate the firing level of rule number 2, firing level of rule number 3, basically inputting the alpha 1, alpha 2, alpha 3 in the antecedent parts. So to combine the rules, what you do is basically you take the minimum of the second consequence with the firing level of the second input, and the third consequence with the third firing level, and you obtain a plate, basically a solid plate like this one. From that one, you can extract its center of gravity, which is basically the x coordinate of the center of mass, if you would look at it as a solid plate with constant density, and that's going to be your output of the system. Yes. So Mamdani systems are nice and very easy to understand. Nevertheless, they are hard to compute. The COG is typically typically time consuming to compute. Yes, even for computers, this will be a task that you don't want to do repetitively at every step. So what you do is what basically Takagi, Sugeno, and Kang have suggested in their work, is to replace it by considering the inputs to be still fuzzy sets, but the outputs to be just constant values. Yes. So if we do that, the output of the Takagi-Sugeno system can be just computed by combining the firing levels with the outputs and getting a weighted average of those. Yes. So if X is AI, then Z equal WI can be translated into this Takagi-Sugeno Kang fuzzy system. So typically this would look like given on the picture. So let's say we want to input a given output. Then for X value input, you would look at what rules are active, and the given rules will output a certain X value. To get the average output, you would make basically a weighted average of the individual rule outputs with their firing level. What you get this way is a system that is close to a neural network. Yes. So it's basically a linear combination. You can look at these as kind of the analog, the fuzzy analog of the activation functions, and these could be the fuzzy analog of the weights in the neural network. So this will be a lot easier to compute, a lot faster. There is no COG here. There is no integral that you need to calculate. And additionally, you can train for W relatively easily in this setting. So, of course, you can get this more complicated. So let's see a little more complicated scenario. So we introduced it in a simple scenario to understand it easier, but typically you would need more. For asteroids game, for example, you would need not only distance to a certain asteroid, but also their orientation. So if asteroid is near and coming towards you, yes, which means some angle could be small, then threat level could be calculated as a linear combination of this type AIX plus BIY plus CI. For easier calculation, you can just ignore AI, BI, saying you can set those to 0 and work on CI, because that's the main. It's enough to have that approximation level at that point. So based on this system, Young has introduced the Adaptive Network-Based Fuzzy Inference System, ANFIS, which is a Takagi-Sugeno fuzzy system that can learn, basically. And then we can use gradient-based methods to train it. Or we could also use least squares learning for some of the things. Here's the official figure from Young's paper. Yes, so you would have two inputs, which means basically two antecedents. And each of the two antecedents has two linguistic variables. A1, A2 are the linguistic variables of the same antecedent, B1, B2, the same one. Then basically you can make a product of those, normalize, and then at the end of the day, calculate the output, just as we have seen in this formula. Yes, with the firing levels being normalized. So what happens then? How do I train this? I can train it using back propagation similar to what we have seen. Yes, so I know the error here. I can basically calculate the error at each level in this graph. Yes, and the easiest to train are the parameters CI. So even with fixed AI, BI, you can train CI and you get a decent answer for different applications. So basically you set up, one can set up antecedents and consequences at the desired resolution. Yes, you can use 3, 5, I don't know how many antecedents, and then the consequences can be organized into a vector, and you can train those using gradient descent learning. So basically, you can look at it and you can typically understand the Takagi-Sugeno system as a fuzzy version of a neural network where X is fed through a network. Then the Takagi-Sugeno part outputs one thing, and then you can basically get the output of the system to be very much like a neural network. So you can train it that way as well. Yes. So now, nevertheless, when you have a Takagi-Sugeno system, you've got yourself some constants that are trained, and you lost some of the explainability that is very easy to have in the Mamdani version. So then, basically, we want to have basically an expert looking at it and doing it in an explainable manner. So the Takagi-Sugeno system, we convert to a neural network, then we train it basically, the ANFIS, and we've got a new neural network. To make it more explainable, we need to convert it back, yes, and then the expert could analyze what's going on. Yes, how to do that? This is possible via different methods. We can approximate a Takagi-Sugeno system with a Mamdani method. Yes, so Takagi-Sugeno system is nice, but not as explainable as Mamdani. So instead of saying if velocity is low, then acceleration is high, it would look like if velocity is low, then A equals 17. Yes, what means 17? That's basically what the following slides try to explain. We can optimize this using the following trick. We can transform a Takagi-Sugeno back into a Mamdani system, basically looking at the rules and coming up with kind of values that are obtained from there. So we have an approximation theorem where you can actually convert the Takagi-Sugeno system to a neural network. Then the neural network is trained. Yes. Then it's giving you back a Takagi-Sugeno system. Then you approximate it with the Mamdani system. There's an inter-approximation. Basically, the TS and Mamdani are basically working together to explain the system. And the Mamdani system, now the expert could look at and understand what's going on. Yes, and yeah. So, for example, I can imagine it this way for you to work for the asteroid example. You would have a Mamdani system that would look at threat levels, yes, for each asteroid. And variables, just an easy version could be distance and angle. Yes, if distance is small and angle is small, it's between, well, okay, the angle could, angles near 180 basically, towards you, coming towards you. The angle from the asteroid towards you and between your position vector. So if those angles are small and the asteroid is near, then threat level is high. So instead of saying threat level high, the Takagi-Sugeno system would give you a numeric value. Yes. So maybe then the Mamdani system would actually interpret that numeric value as high, low, or medium, or what what you want to do. All right, so where does this method work? So we have used this method for certain example. We worked on the prediction of the El Niño Southern Oscillation, improving prediction of the El Niño Southern Oscillation using this training method. So we trained the Takagi-Sugeno for that. So how that looks like, El Niño Southern Oscillation is basically the El Niño phenomenon, which modifies global climate. No, the weather influences the weather. So climate is the long-term thing and weather is the shorter thing. So my scientist colleagues always make me this correction. So climate is the long-term behavior and weather is the short-term behavior of the same system, basically. So El Niño is a long-term behavior that basically drives the short-term behaviors as well. So to predict El Niño is very important, and how it's done, you would have various models. It's an ensemble model, and we have various models, and you try to combine them into one single prediction. And how we can do that? Basically, we could have antecedents. So what we want to do is basically to rate the models based on their importance. What models have better success in prediction should get higher weights in the system. Yes, so that's the easy Mamdani rule that we can imagine. So here's an example in the third bullet point. If a model's historic error is low, then its weight in the prediction is going to be high. Yes. So antecedents, we worked with homogeneous spread on the domain. Low, medium, high, and high. And we looked at historical error. And we got a Takagi-Sugeno system. So first we got a Mamdani system with rules of this form, then translated into the Takagi-Sugeno system corresponding to that. Yes. Then we learned the parameters of the system that gives the best prediction. Yes. So putting everything together, we can see that we got a model that is linear in the coefficient Cj of the model. So what do we have here? Here we have the Takagi-Sugeno-Kang system output, which is basically firing levels with the typical outputs, but the input values correspond to model inputs, and basically those are weighted in the model outputs. So we have a combined behavior at the end of the day for the prediction of the ensemble to be influenced by these parameters Cj. Cj are then good candidates for least square learning. So we did the least square learning. So if you put everything in matrix form, we got basically the error to be expressed like this, where A, C, and Y are given from the data. You can learn all these from the data. And the error is minimized using this prediction, the normal equation that we went over. So this is able to learn the Cj parameters of the system, but that's not enough. We want to learn the antecedents as well. So what we were doing, basically, we use least squares learning for the antecedents. Yes. So for the antecedents, we basically applied an online learning method. basically we modify the weights a little bit. We approximate the gradient via what is it called? Finite difference kind of scheme, and that gradient we use for improving our weights. Yes. So basically what we do is we modify all the parameters with a little bit in a certain direction. Then we recalculate that the error based on the modified weights. Then we basically calculate the gradient based on that. And this is an approximation only, it's not going to be an exact gradient. Then we update the weights using the well-known gradient descent equation. So now what happens is in our system, when we modify the weights of the system, we modify the values of the antecedents. So my CJ are not optimal anymore. So I need to alternate between least squares learning and gradient descent learning. Yes, so at this point, we can just do that. So least squares learning and gradient descent learning alternate in order to get you the best prediction possible. Yes. So now some graphs to the extent of the efficiency of the method. So the orange is the real data. So we want to predict the El Niño coefficient, which is the orange one. Green one is basically the system data, the trained data on the learning period. Yes, so we learn over the 8 months here. And we basically have the blue one to be the just normal average. Normal average is the blue one, that's the conventional method. And the green one is our method. And well, the green one at this point is more intelligent than the blue one because it knows what's the output. So we don't want that. So what we do is we stop at this point when the green one ends the training, and we let the prediction go with the trained parameters. And the red one is actually current, the prediction that we want to, the prediction of the El Niño coefficient, El Niño constant is coefficient based on the model. So this red part is where you can actually compare. So orange is the real data, blue is the prediction, and the red is our prediction. And it's better with the Takagi-Sugeno system. We can improve in this situation the results. Okay, that's not always that easy. Here's an example where we did score worse than the average. So orange is again the actual model, blue is a conventional method, and red is our fuzzy system output. Yeah, this one actually, blue one was better. But on average, we have our method better. Here again, ours was better. So red one is ours, orange is the real one, blue is the conventional method. So the Takagi-Sugeno training works. It can reproduce better the methods on the output. Okay, and what we can also do at this point, because we have conversion between Mamdani and Takagi-Sugeno, we can look at what we have learned, and we have learned that basically the antecedents were this way initially, and after learning they became this way. Yes. So what we can see is there's a big resolution difference between low, high, and the near zero region. So the model is able to focus its attention to those models that are having near zero And those were many of them. Therefore, they will get more details there. Yes. So the error got more detailed in this setting. This is the average error and the model error, and in most situations we have better error, except for this setting when it's worse, but we have less, very limited learning has been done, so we don't have enough learning basically at this point for the model. Yes. So gradient-based methods can balance exploration versus exploitation in the asteroid game as well, and they have been used extensively in training fuzzy systems. For gradient-based methods to work well in the competition setting, they need to be probably combined with reinforcement learning. So I don't see how. Yeah, probably that's the best way, because you don't have really data on which you could base a supervised learning. So you don't have a perfect player who plays the game and wins all the points and then mimic that player. And you don't want to do that, because what if your opponent learns the same way but improves a little bit better? So we want to have a second seminar on reinforcement learning. So basically that's when we will combine the gradient-based methods with the reinforcement learning algorithms and get basically a general fuzzy reinforcement learning algorithm to be the goal for the two seminars. So the fuzzy reinforcement learning method works nicely on different applications, and you can see that next seminar. So I little bit made a made a little bit of an advertisement of my next seminar that will be Friday, if I correct. Yeah, these are my references. Yeah. Thank you very much, and I'm looking at questions if you have questions.
Yeah, so we'll go ahead and do a short Q&A session. If others want to put their questions in the chat, or just raise your hand, I'll get to you, but I'll go ahead and start us off. Dr. Bede, you mentioned doing least squares optimization on the input membership functions, if I understood you correctly, much like ANFIS. I was curious what your thoughts were with backpropagation to and potentially through the input membership functions instead of only using that for the rules.
Yeah, so least squares, because least squares applies only to linear. Maybe I could go here. I like to scribble while thinking about an answer. So least squares applies to linear layers. So basically, this is specifically linear method. So for the so when we have the ANFIS architecture, let's say, we have basically the ANFIS membership functions here, and we have X, the input, yes. Then the weights over here, W1, W2, Wn, we can train using least squares. The parameters here, let's say this is B1, B2, B3, parameters of the fuzzy the membership functions are hard to train via the least squares method. What was successful? Well, was what we did with Markel in this this example that I had shown you was basically using an approximation like this, del E del B1, for example, that can be approximated with E with a modified B value minus E original B value divided by what is the change. So we approximated the gradient with that, kind of an online method, and then did the backpropagation B1 equal B1 minus eta times this approximation that we've got. So this works okay at some level and avoids the big pain, which is basically gradients with respect to these parameters are hard to calculate and are unstable because they are basically breakpoints in the fuzzy sets. So they are not nice, differentiable, not smooth portions of the graph of the thing. But what also could work, what it also works in a different setting with Ben van Oostendorf and with Ben we looked at basically with and Eric Zender. Yes, so they are competition winners from 2 years ago, basically. So what they looked at in a different application, they looked at basically using PyTorch to have the weights. You could still train least squares, but using PyTorch, you can implement this ANFIS. So basically, you can implement ANFIS directly in PyTorch, and then PyTorch has a So basically, they implemented it in PyTorch. And then in PyTorch, there is an autograd, automatic differentiation method. Autograd basically calculates the gradient with respect to B1 parameters, these inside parameters using automatic differentiation. Automatic differentiation is a method how basically you use chain rule to differentiate code. So code will actually do, for example, here B1 plus B2. Then at some point it's going to take B1 square. Then going back through the code, you can actually take the derivative at each step. This is 1, the derivative. So you can actually differentiate code with the so-called automatic differentiation. So autograd method in PyTorch allows you that. So basically they use the autograd to train for these input parameters. And you can do that with multiple layers. So we can imagine now an ANFIS with multiple layers of Takagi-Sugeno systems. Yes, so this is an input to the next one, and the input to the next one. Yes, so multiple layers, and autograd works for all of them, just like in deep learning. So that's possible. Yes, so there is research going into that direction. It was not used in the asteroid game. It was used in a different application. Typically, like they use it in
Supervised learning.
Inverted pendulum example.
Okay.
Yeah, so basically you can balance an inverted pendulum on a cart with this method. So it works nicely, but it's still there is lots of work to be done in that direction.
Gotcha. Well, thank you for that. And there was a paper on that from Eric and Ben.
I think its latest NAFIPS paper was about that from Eric and Ben and myself. Yes, I will try to find it. If you would like, I can send it to you.
Yeah, if you don't mind, I'll add it into the description for the recording on YouTube. Well, I don't want to take up all the time. Would anybody else on the call like to ask any questions from Dr. Bede? I'll add that having this capability, if you can calculate gradients based on your whatever architecture and function approximator you're using, it's often a good thing to do because there's a lot of information in the gradients. So where you can, I would recommend doing so. So this type of methodology is pretty powerful, not just for your Kessler development, but like Dr. Bede said, in many supervised and reinforcement learning problems, it's the basis for most modern machine learning methods involving neural nets.
Yes, and this automatic differentiation method, I didn't know back in a couple of years ago. I attended a conference where the team developing the AutoGrad method was presenting. They were looking for funding because, well, they were developing this awesome method, but no one wanted to fund them because they didn't imagine the applications that could go from there. And since then, this is the basic method in PyTorch for taking gradients. So they have actually created something really awesome.
Yeah, that is fascinating, being able to differentiate code directly. But I'll leave that for another topic.
Yeah. Indeed, more research in that direction will be interesting to do.
All right. If we don't have any other questions for Dr. Bede, we'll go ahead and wrap things up. Reminder that we have another talk from Dr. Bede on Friday on reinforcement learning in fuzzy systems. So that one will be an extension of this, where we talk about, after you can do backpropagation, what can you do with that in terms of learning from your environment. I highly recommend everybody join that live to ask questions. But yeah, with that, we'll go ahead and close out today. As always, this recording will be on YouTube, and we'll see you in the next seminar. Thanks again, Dr. Bede, for joining and giving a wonderful seminar.
Thank you, Dr. Arnett, and thanks for inviting me, and sorry for the problems at the beginning.
No
I
problem.
tested my technology earlier on Friday. Thank you.
No worries. Thanks again. All right. Bye, everybody.
Bye. Bye, everybody. Thanks for attending.